You know, we plug things in all day long. Heaters, fans, our phones, but do we really get what's happening behind the plug? Today, we're going to pull back the curtain on electric power and find out what happens when you ask for a little too much of it. Let's dive in. You've seen it a million times, right? That's 60 watts printed on a light bulb. Well, it's not just a random number. It's a key piece of information. And when a fuse blows, yeah, it's annoying, but it's actually physics acting like a secret bodyguard for your home. By the end of this, you'll get the science that's happening inside your walls every single day. So, here's our game plan. We'll kick things off with the big one. What even is electric power? Then, we'll see it in action on a real light bulb. From there, we'll figure out what your electricity bill is actually charging you for and take a peek at how your home is wired. Finally, we'll get into the dramatic stuff, overloads and short circuits, and meet the tiny hero that stops it all, the fuse. All right, first things first. Let's start with the absolute foundation of all of this. What exactly is electric power? Everything else we're going to talk about today is built right on top of this idea. Okay, so here's the key thing to get. Power isn't about how much energy you use, but how fast you're using it. Think of it like this. The energy is the total amount of water in a glass. The power is how quickly you're chugging it down. So a really high-power device, like an electric kettle, is basically gulping down energy at a super fast rate.
So how do we put a number to this? Well, it all starts with a basic idea. The work done in a circuit is just the charge, Q, times the voltage, V. But remember, power is all about the rate, how fast it's happening. So we divide everything by time, T. And watch what happens. This is pretty cool. Work divided by time, that is literally the definition of power. And charge divided by time, well, that's just the definition of current. So bam, we're left with our master formula, power equals voltage times current, P equals VI.
But what if you don't know the voltage? Or maybe the problem doesn't give you the current? No problem at all. This is where our old friend Ohm's law comes to the rescue. We can just mix and match. If you substitute V with IR, you get our next formula, P equals I squared R. Or if you substitute I with V over R, you get our third one, P equals V squared over R. So really, you have a toolkit with three options. You just have to pick the right tool for the job based on the info you're given.
Okay, enough with the abstract formulas. Let's make this real. Let's see how this math actually works with something you see literally every day, a plain old light bulb.
So you look at a bulb and it says 60W, 120V. What is that actually telling you? Think of it as the bulb's promise. It's saying, hey, if you connect me to a 120-volt source, I promise I will use 60 joules of energy every single second to make light and heat for you. It's a performance guarantee, but only if you hold up your end of the deal and give it the right voltage.
Now, that little label gives us enough information to play detective. We can figure out a hidden property of the bulb itself. So, what is its resistance?
All right, let's think. We know the power and we know the voltage. Which of our three formulas connects those two things with resistance? Yeah, that P equals V squared over R1. We'll just shuffle it around a bit to solve for R, which gives us R equals V squared divided by P. Now we just plug in the numbers. That's 120 times 120 on top, divided by 60 on the bottom.
And what do we get? 240 ohms. See? That rating isn't just a label, it's a secret code that tells you the fundamental electrical properties of the bulb.
And this is why getting the voltage right is so incredibly important. Let's say you take that same 240 ohm bulb and connect it to a little 12-volt battery. Well, the power output absolutely collapses, down to just 0.6 watts. You would barely even glow. The bulb's resistance is fixed, but the power it actually delivers, how bright it gets, is totally dependent on the voltage you feed it. Speaking of all this power being consumed, that naturally leads us to the part nobody loves, paying for it. Let's connect this physics directly to your wallet. If you look at your electricity bill, you won't see watts. You'll see this other unit, the kilowatt hour or kilowatt hour. So what is 1 kilowatt hour? It's simply the total amount of energy you use when you run a 1,000 watt appliance like a powerful hair dryer or a small heater for 1 full hour. So how much energy is that in, normal physics units? Let's do the math. 1 kilowatt is just 1,000 watts, which means 1,000 joules per second. And 1 hour is 3,600 seconds. You multiply them together, and you get 3.6 million joules. That's a huge number, right? That's how much energy is in every single unit the power company charges you for. Okay, so we've talked about a single bulb. Now let's zoom out and look at the big picture, the entire electrical system that's hiding behind the drywall in your home.
Here is probably the most critical concept for home electricity. It's all wired in parallel. This design is fantastic because it means every single socket in your house provides the same full voltage, let's say 240 volts. But it comes with a really important consequence. Every single time you turn on another appliance, the total amount of current being pulled into your house from the main power line goes up.
Think of it this way. The main line coming into your house is like a big river of current. Every appliance you switch on is like digging a new channel to divert some of that water. So the total flow of the river has to be equal to the sum of all the little channels. Every device you turn on adds to the total demand for current. But what happens when that total demand gets too high? What happens when you try to divert too much water from the river at once? Well, this is where we can get into some serious trouble.
You see, the copper wires inside your walls can only handle so much current. They have a safe limit, maybe 20 amps. If you plug in too many high-power things at the same time, like your microwave, a space heater, and a vacuum cleaner, the total current you're demanding can go over that limit. The wires just aren't thick enough to handle that much electrical traffic, and they start to get dangerously hot. That's an overload.
Now, it's absolutely crucial to know the difference between an overload and a short circuit. An overload is a too much stuff is turned on problem. The wires get hot, but it's usually kind of a slow process. A short circuit is a completely different animal. That's a catastrophic failure. It happens when the live wire accidentally touches the neutral wire, creating a super low resistance shortcut. Ohm's law tells us if resistance plummets, the current skyrockets to an insane level instantly. That causes sparks, melting, and is a major, major fire risk.
So, if these dangers are real, how do we protect our homes from them? Well, we use a very simple but totally brilliant little invention. And that is the absolute genius of the fuse. It's basically just a special, thin piece of wire that's intentionally designed to be the weakest link in the whole circuit. All the electricity for that circuit has to flow through this one tiny wire. And this wire is made of a metal with a really low melting point. So if the current ever gets too high from an overload or a short circuit, that little wire gets incredibly hot, way faster than anything else, and it just melts. By melting in half, it creates an air gap, which completely breaks the circuit and stops the flow of electricity dead in its tracks. It literally sacrifices itself to save your home. So let's wrap this all up with the ultimate exam cheat sheet. Number 1, you need to know your 3 power formulas and when to use them. P equals VI, P equals I squared R, and P equals V squared over R. They're your best friends. Number 2, remember that conversion. 1 kilowatt hour from your bill is a massive 3.6 million joules. And number 3, the big safety concept. In a parallel circuit like your house, the voltage is always the same, but the currents from each device add up. If you can master these key points, you'll have a real solid understanding of the electrical world all around you.